Today we're going to be talking about exponential equations or exponential functions. We've kind of started talking about this a little bit with our geometric sequences, and we're going to actually see a lot of similarities between geometric sequences and exponential functions. But let's get going. So an exponential function is a function that has a variable in the exponent. Oop, and my marker's a little fat at the moment. In the exponent. So as you can see, there is our equation, f of x is equal to a times b to the x. Okay, let's kind of talk about what a couple of these different numbers mean. So a, it's that number in front. Our a is our starting value. Okay, so it's the starting value. It's where our graph is going to start with, whatever base amount that we're going to start with. It also has the nice little effect on our graph of being the y-intercept. And another name for our starting value, we could also call it our initial value. Okay, so starting value, initial value, and it happens to show up on an actual graph as the y-intercept. Okay, then over here on the far right, our x, that is our exponent. Which is our x. And remember, we always know x is our independent variable. And it being an independent variable, specifically a variable, means that it is something that changes. So the exponent is what we're going to plug into our function that actually is going to make things change. We're going to plug in different x values to get out different y values. Remember, just like with linear, where we plug in x and get out y, plug in independent, get out dependent, we're going to do the same thing with exponential, it's just a slightly different function. Okay, the last but not least is our b. Our b is very important because it is our base. It's kind of what affects our entire graph. Okay, and we have two different kinds of base. We can have a growth base, or we could have a decay base. Okay, and what that means is that I can either have a base that's going to make my function grow in value as x goes up, or I can have a base that's going to make my function decay or decrease in value as my x values go up. Okay. So to help separate them, if my b value is greater than 1, so if I have 1.5, 2, 4, 20, anything greater than 1, then that's going to be growth. Okay, if my b value is in between 0 and 1, then that's going to be decay. So any sort of fraction or decimal, so 1/2, 1/4, 1/3, 0.5, 0.7, 0.1, any of those sort of things, any decimal or fraction in between 0 or 1 is going to cause decay. Now you might notice, what did I leave out? Well, I left out 0, and I left out all of my negative numbers. Okay, and that is because b must be positive. Okay, so that is very important. B must be positive for us to actually have a exponential function. If b is not positive, it's going to do all sorts of wonky things. So we always want it to be positive. Okay, so now let's actually graph some functions, just like we did for our initial or for our linear functions. We're going to be graphing exponentials, talking about their graphs, all that sort of stuff. So we have three different functions. Let's start out with f of x is equal to 3 to the x. Okay, so just to help kind of make this easier to read, this is 3 to the x. Okay, and we type it in. I'm just going to show you in your calculator real quick. Okay, we type it in as 3, 2, where's my caret sign? There we go. To the x, like that. Okay, so that's kind of the shape that we're going for right there. That is our exponential function. Now we're going to actually talk about how to graph this by hand, but the nice thing is you're always going to have this Desmos calculator, so you can just stick your exponential function in to kind of see the shape and see what the graph is going to look like. Okay, so this would be 3 to the x, or of course, if we wanted to be more specific, f of x equals don't know why it didn't. There we go. F of x is equal to 3 to the x. Okay, so same exact graph that we had there before. Okay, now let's actually graph these points. And if I wanted to get these points, okay, remember back over on our notes, we're going to be filling out our table down here. Okay, and I'm just going to fill it out for our basic x values: 0, 1, 2, 3, 4, 5, and 6. Okay, so what we're going to do is we're going to practice plugging in those x values to get these y values. So I'm going to plug in 0 for x and get out whatever y gives me. Okay, so 3 to the 0 is equal to 1. So I'm going to come over back to my notes. Right here at 0, our y value is 1. Okay, then coming back over to my Desmos calculator, I can just go up here, and instead of 0, now I'm going to put in 1 because that's my next x value. Okay, so now it's 3. So 3 to the first is equal to 3. So my next x value is 2, so I'm going to come back to my Desmos calculator, take away 1, put in 2. Now we're 9 because now I have 3 squared. So it's an exponent. So remember, an exponent means how many times to multiply the base. So first time I didn't multiply the base at all. That's why I got 1. Second time I multiplied the base just once. So just 1, 3 is 3. This time I'm multiplying the base twice. So 3 times 3 is 9. Okay. So hopefully you should start to kind of see the pattern. I'll finish it out in the Desmos calculator anyways, just so we can see it. So 3 to the third would be 27. 3 to the fourth would be 81. 3 to the fifth will be 243. And 3 to the sixth should be pretty big, will be 729. Okay, so now let's talk about this a bit. So some things you should notice just from our table. And remember, this is a table of values, our x values and the y values we get out. Okay, first and foremost, right here, where x is equal to 0, y is equal to 1. So what do we call that? That is our y-intercept. Okay, where else do we see 1 in our problem? Well, remember, from our formula, our y-intercept is the a value, and the a value is the number that's being multiplied in front of b. Okay, so we don't have it written, but what number is technically here in front of the function? It is technically a 1. Okay, so same thing here. We have a 1, so our y-intercept should be 1, which that lined up with what we got from our values. When x is equal to 0, y is equal to 1, which is what the y-intercept would be. Okay, so the next thing you should notice, each time to go from y value to y value, okay, we are multiplying by 3. Okay, where do we see 3 in our problem? Well, 3 is our base. So 3 is equal to our b value. 1 is equal to our a value. So a, remember, is our starting. B is our base. It's the number we multiply. It's the number we're growing by. So because my base is 3, which is a base value greater than 1, this is a growth function. So my b value is greater than 1, which means it is growing, which, as we can see from our values, as we go up in x value, our y values go up. So that all lines up. It's a growth function. Our y values are growing as x grows. This all is starting to make sense. Okay, so now let's actually put some of these points on our graph. We already kind of know the general shape of it. It's going to do that swoop from left to right. Okay, so at 0, we have a y value of 1. At 1, we have a y value of 3, and I'm just pulling these values from the table. And at 2, we have a y value of 9. 7, 4, 5, 6, 9. And then after that, we're basically off the page, yes? Okay. So the last thing we need to talk about is what's going to happen if we go the other way. So think about it. If going this way, I am multiplying by 3. To go the other way in my table, I would have to divide by 3. So what would happen if I kept dividing by 3 in the other direction? If I kept going as my x became negative, I kept dividing by 3. Well, if I kept dividing by 3 over and over and over again, 1 divided by 3, then that divided by 3, then that divided by 3, my number would be getting smaller. Okay, but my number is never actually going to be negative. Okay, so dividing by a positive value of 3 is never going to make a positive number into a negative number. So what that means is as we go over here, my graph to the right, we already talked about this, it's going to kind of swoop up. Okay, my graph to the left, it's going to get really close to 0, but it's never actually going to cross 0 and become negative, and it's never going to actually equal 0. And we can see this over on our Desmos graph. You can see here, okay, our exponential function, it gets really close to 0, but it never actually equals 0. Okay, if I zoomed in, see how even when I zoom in really, really close, it's close to 0. And the further I go out in the x direction, it gets closer. But then as I zoom in, it's still not crossing 0. So I could do this all the way out to like super huge numbers. So I'm here at negative 6,000. And even when I zoom all the way in at negative 6,000, that's the closest it will get me. Okay, you can still see it looks like it's really close to 0, but it's still not equal to 0. Okay, so that is very important. We call this this thing that the function is doing where it never actually quite equals 0. We call it approaching an asymptote. An asymptote is this nice little imaginary line that guides our graph. So we have an asymptote at y is equal to 0. Okay? And that is kind of how we do an exponential function. Let's look at another one. Okay? So over here we have g of x is equal to 2 times 1/2 to the x. Okay? So same thing. We're going to put it over here in our Desmos calculator. So we have 2 parentheses 1 divided by 2 and then we want to raise it to the power of x. Okay, so now, similar function, but now we flip the other way. So now, as we go from the left to the right, our function is going down. Well, some things you should notice, okay, our b value is now 1/2. 1/2 is in between 0 and 1, okay? Because 1/2 is in between 0 and 1, we're now going to have a decay function, okay? Now let's do the exact same pattern we did last time. We're going to find values of x, 0, 1, 2, 3, 4, 5, 6, and we're going to use those to find y values. So 2, parentheses, 1 divided by 2, close no, not there. Close parentheses, raise it to the power of 0 would be our x value. So our first one is 2. Okay, then if I raise it to the power of 1, next one will be 1. Then if I raise it to the power of 2, next one would be 0.5, which is the same as 1/2, right? Then if I raise it to the power of 3, .25, which is the same as 1/4. Okay, hopefully now you're starting to see what's happening. Every time I'm dividing by 2, or more specifically, I'm multiplying by 1/2. So hopefully you get to a point, y'all, where you can start to kind of fill these out without using the calculator. So if I just kept multiplying by 1/2 or dividing by 2, then I could finish out my table like that. Okay, so once again, some things to note. My a value this time, okay, is 2, which means my y-intercept is 2. My b value this time, what I'm multiplying by, is 1/2. Okay, which is in between 0 and 1, which means I am decaying. So let's add it up here on our graph. Okay, at 0 we were at 2, which was our y-intercept. Then we went from there to 1, then 1/2, then 1/4, and 1/8, and so on. So same thing we talked about the last one, y'all. We're going to get really close to 0 without ever actually equaling 0. Because like 1/32, then it would be 1/64, and so on and so forth. And there's our exponential function. Okay, same sort of shape as we did last time, but now it's going the opposite way. It's decaying from left to right. Okay, and just like we talked about last time, we should have that asymptote at y equals 0. Okay, last one, and I'm going to pause myself real quick and see if y'all can fill this one out without me using your calculator. Okay, so go ahead and pause me. Try to do this one on your own using your Desmos calculator, and then unpause me and see if you get the right numbers. All right, y'all. So hopefully you were able to fill out your table the same as usual. So we're going 0 to 6. Our first value was 1/4 because as we can see, 1/4 is that number in the front of the function. Then we're multiplying by 3 each time because 3 is our base. So 1/4, 3/4, 9/4, 27/4, and so on and so forth. And our graph this time, because 3 is a value greater than 1, our graph is once again growth. So this one's a little bit of a trick because the a value is 1/4. So the initial, the y-intercept is a number between 0 and 1. But the b value, the growth factor, is still greater than 1. So we're still growing by multiplying our number by 3. It just starts really small. Okay. And then as it gets super big, 729 to the fourths, to the right, to the left, it would be getting really small. So 1/4, then 1/4, divide by 3, divide by 3, divide by 3, just like we did for the first one. Still not crossing that asymptote of y equals 0. So what pattern do we notice in the tables? Well, hopefully at this point you've started to notice that it is a geometric pattern. Okay. Exponential tables have a pattern that is increasing geometric, which is our growth, or decreasing, which is our decay. Okay, so all of these are all geometric patterns. We're multiplying in between terms by that base value. All right, now let's look at an exponential function versus a linear function. So we have two functions, y is equal to 3 to the x, and y is equal to 2x plus 1. And we're going to graph each of them here. So our y equals 3 to the x, we've already graphed that one before. So 0, 1, 1, 3, 2, 9, 4, 5, 6, 7, 8, 9. Just like that. And we know we have an asymptote here. And then our linear function, we've graphed those before. So we have the function 2x plus 1, so y-intercept at 1. And slope of 2, which means we're going to rise by 2 and go up by 1. You can also just plot the points that are listed up here in the table. That's fine too. And then once we do that, we can add in our nice line. Okay. So some differences we should note out. They're both increasing naturally. They're parent functions. They're both increasing. But the big difference we should notice is the difference in their relationship. Okay. Our exponential functions, they increase exponentially where we multiply by a number each time. So in this case, we're multiplying by 3. So while they start kind of with similar growth patterns, 1, 3, 1, 3, pretty quickly by 2, we're at 9 and 5. By 3, we're at 27 and 7. And by 4, we're at 81 and 9. So our exponential function is growing exponentially faster. So what is the difference between exponential and linear? Exponential increases exponentially. Because remember, it is our number raised to the power of x. While our linear function, what have we learned about slope? Well, slope is a constant number that we're increasing by. So we're always increasing by that 2 over 1. 2 up for every 1 x value. So linear increases at a constant rate. So constant goes with linear. Okay. Now our asymptotes, we already talked about this a little bit before, is an invisible line that guides a function as it approaches if Mr. Darbellum could spell, infinity. So as it goes out in both directions, infinity and positive infinity, that's what happens as we go out forever in x. Our exponential function is guided. It approaches that asymptote without ever crossing it. Okay. So let's we've talked about graphing exponential functions. Now we're going to talk about if an exponential function is already graphed, what's some of the key information that we can pull. Okay. So looking at this one here, so our asymptote, remember asymptote is the line that looks like it approaches. Well, this one looks like it approaches the same thing that we usually have approached. It has that y equals 0. And we do denote the asymptote as a y equals line, okay? Because it's that horizontal, like that linear line that goes straight through a y value. It's going straight through the y value 0, okay? So our asymptote, y equals 0. Okay, our y-intercept, remember y-intercept is where it crosses the y-axis, it is always a point. So we list our y-intercept as 0, 5 there. Okay. Our domain, so we haven't really talked about this yet, but our domain, did we have any x values that we talked about not being able to plug in? No. Okay. If I kept going forever, even though it kind of looks like it stops off because I keep plugging in x values forever, yes, I could plug in x being 100, x being 1,000, x being 100,000. So it's going to go forever in the positive direction. Looking here, I mean, just looking at our graph, it looks like it's going to keep going forever in the negative direction. So forever in the positive x, forever in the negative x, that would just be our all real numbers, okay? Which you can write as that all real numbers, the r with a line through it. You can write it as all real numbers. Or you can, of course, write in interval notation, negative infinity to infinity, whichever you prefer, okay? Now our range, remember, has to do with our y values. So looking at our y values, well, we already know our asymptote is the lowest it can get, right? Okay, it's not ever going to cross the asymptote. Well, as it keeps going up, okay, looks like it's going to go on forever. So I would just say my range is all y values that are greater than my asymptote, which my asymptote is 0. So my range would just be y is greater than 0. Okay, so domain is always all real numbers. So no matter how much our exponential functions change, the domain is always going to be all real numbers. Our range is always greater than or less than the asymptote. So just depending on where the asymptote is, where our function falls, our range is always going to be y values greater than the asymptote or y values less than the asymptote. It's never going to be any other value than the asymptote. So let's look at our next one. So this function here, first of all, our asymptote, what y value does it look like it's sloping off at? Well, it looks like it's sloping off at 3. Okay, and I even gave you the function this time so you can see that plus 3. That's probably where that asymptote comes from in our function. So our asymptote would be y is equal to 3. Y-intercept, what y value does it cross the graph at? Well, it crosses the graph right here at 1, 2, 3, 4. So our y-intercept would be 0, 4. For our domain, we just said this, domain is always all real numbers. And then our range is y is greater than or less than the asymptote. So our exponential function is above the asymptote, so it's going to be y is greater than 3. Okay. And just a reminder, y'all, it's not greater than or equal to, because remember, we can't equal the asymptote. It's bounding our graph. We're not going to be touching or crossing it. Okay. Then last but not least, this function, where does it look like it is sloping off at? Looks like we're back at 0. So y is equal to 0 is our asymptote. For our intercept, we're crossing, which deceptively looks like it could be 1, but it does go down to -4 here and then 0. So 0, -4, halfway would be -2. So y-intercept would be 0, -2. Domain, always all real numbers. Range, our asymptote is 0, but this time our graph is below the asymptote. So our range would be y is less than 0. All right, y'all. Those are exponential functions, how to graph them by hand and how to kind of analyze their graphs. Please, please, please ask more questions in class. Your teacher will go over this. But that is exponential functions in a nutshell.